All right, so this is going to be our walkthrough for the homework assignment titled Finding Local Extrema and Intervals of Increasing and Decreasing. So we're looking for local maxima and minima and when functions are increasing and decreasing. So in order to do that, we first just need to take a derivative of each of these functions. So we'll start with finding f prime of x, which will be 3x squared minus 4x. To find when this is potentially at a max or a min, we need to see when it's equal to 0, and we also need to see when it's undefined. We'll note that f prime is never undefined, right? Because it's just a polynomial function. So it's never undefined, so we're not getting a critical value from when the derivative is undefined. To figure out when it's equal to 0, we're just going to factor out the x from this, giving us two critical values, right? One is going to be x equals 0, and the other one is going to be x equals 4/3. So in order to determine if those are maxima or minima, we always want to build a sign chart here, putting the two critical values on it. And then we'll test values that are on each of these intervals to see if our derivative is positive or if our derivative is negative on each interval, because that will tell us if the function is increasing or decreasing. So first we'll pick something between 0 and 4/3. So I'm going to try something like x equals 1. If I plug x equals 1 into my derivative, I get x, which is 1, or a positive number, times 3 times 1 minus 4. Well, 3 times 1 minus 4 is a negative number. So I get a positive number times a negative number, which tells me that the derivative is negative, and it tells me that the function is decreasing. So I'm going to draw on here, it's like blue. The function is decreasing there. Then I'll pick something more than 4/3. It doesn't really matter what it is, as long as it's more than 4/3. I'm going to pick a million. Right? If I pick a million, right, I end up with a positive number for x, right, this x. And then 3 times a million minus 4 is also positive. So we get a positive number here, which tells me that my function is now increasing because the derivative is positive. And then if I pick a negative number, like negative a million, I end up with a negative number from my derivative, x, times another negative number, which a negative times a negative is a positive, and we'll end up with f increasing. So we should be able to see that our function has a local maximum at 0, and it has a local minimum at 4/3. Well, we need to find those two values. So first we need to find f of 0, which that one's pretty straightforward. It's 3. And then we need to find f of 4/3. So we're going to plug that into the original equation. 4/3 cubed minus 2 times 4/3 squared plus 3. I'm not going to go through all the arithmetic there, but that comes out to be 49/27. So we've got a local max of 3 at x equals 0. We have a local min of 49/27 at x equals 4/3. And then we also need to state when this function is increasing and decreasing. So it's increasing whenever the derivative is positive, which was from negative infinity until we got to 0. And then it was increasing again from 4/3 until infinity. And the College Board always indicates their increasing and decreasing intervals with brackets. So we're going to use brackets for all of them unless it's at infinity values or values that are the end of an open interval. And so then we're going to be decreasing on all the other intervals, which is just the singular interval from 0 to 4/3. And so that's our answer to number 1. Our second one here, we're going to go through the exact same process. So we'll first take a derivative, giving us 4x cubed minus 4x. We'll note that that is never undefined. Right? Again, it's just a polynomial. But it does equal 0 a few times. So we'll factor out the 4x from this, giving us an x squared minus 1. And we can see that it's x equals 0 and x equals 1 and negative 1, but I'm going to rewrite it as 4x times x plus 1 times x minus 1 equals 0, giving me x equals 0, x equals negative 1, and x equals 1. And the reason I'm writing in the fully factored form is because in a moment I'm going to put these all on a sign chart. In fact, we'll start doing that right now. We'll put them on the sign chart, and when I do that, it's really nice to have it in the fully factored form because it makes it a lot easier to figure out what the product of all the numbers is if I don't have to deal with squaring stuff, like with the x squared minus 1. So we'll test our intervals with our 3 critical values. Again, just like the last problem, we're just plugging these numbers, a number that's between 0 and 1, into this factored form of our derivative. So if I take something like a half that's between 0 and 1, and plug it in here, 4 times a half is a positive number. A half plus 1 is a positive number. And a half minus 1 is a negative number. Well, 2 positives times a negative is going to give us a negative. Okay? And if I take something like more than 1, like 1,000, I'm going to have a positive number from the 4x, a positive from the x plus 1, and a positive from the x minus 1. So that's going to end up being positive times positive times positive, which is positive. And then if we take something like negative 1/2, well, that's going to give me, negative 1/2 is going to give us a negative when I multiply it by 4. And when I add 1 to negative 1/2, I'm going to get a positive. And when I subtract 1 from it, I'm going to get a negative. Well, 2 negatives and a positive makes a positive. And if I plug in something less than negative 1, we're going to end up getting 3 negatives here, right? Like if I plug in negative 1,000,000, 4x, x plus 1, and x minus 1 are all negatives. 3 negatives multiplied together make a negative. And so we can see that our function decreases, then increases, then decreases, then increases, right? That's what f is doing because the derivative goes from negative to positive to negative to positive. We'll need to find the values of our function at 0, negative 1, and 1. F of 0 is an easy one. It's just 8. Right? Just plug in 0 to your original function up here. F of 1 ought to be 1 minus 2 plus 8. 1 minus 2 plus 8 ought to just be 7. And then f of negative 1 is an even function, right? Even powers on everything. It's going to end up being the same thing, right? Because negative 1 to the 4th is still 1, and negative 1 squared is still 1. So we end up with the same exact value there. And so that's really all we need to do to plug things in. So now all we need to do is just write out our answers. We're going to have a local max of 8, right? That's our value at 0. So local max of 8 at x equals 0. And a local min of 7 at both x equals 1 and x equals negative 1. And then our function is decreasing from negative infinity until we get to negative 1. And it's also decreasing from 0 to positive 1. And then our function increases from negative 1 to 0, and again from 1 to infinity. And that should be it for our second one here. All right, for our third problem, once again, we're just going to start off by taking the derivative here. So we will find our derivative using the quotient rule this time. So f prime of x ought to be x plus 3 times the derivative of the numerator, which is 2x minus 2, so v du, minus u, so x squared minus 2x plus 1, times the derivative of v, which is just 1, all over x plus 3 squared. And then we'll simplify down that numerator a little bit. So it looks like that becomes a 2x squared plus a 6x and minus a 2x ought to be plus 4x minus 6 minus x squared plus 2x minus 1 when I distribute the minus sign through everything. And so our derivative ends up simplifying down in the end here to x squared plus 6x minus 7 over x plus 3 squared. And so all we have to do then is see when that's equal to 0 and when that is undefined within the domain of our function. We'll note that the domain of our function is x cannot be negative 3, right? Because that would make the denominator 0. And so this f prime is not undefined on our domain, because the only thing that would make it undefined would be if x was negative 3. And we can see clearly that negative 3 is not in our domain. So f prime equals 0 will be our next thing to do here. F prime of x equals 0 whenever x squared plus 6x minus 7 equals 0. Well, we should be able to factor x squared plus 6x minus 7 into x plus 7 times x minus 1, which gives us x equals negative 7 and x equals 1 as our two critical values. So we've only got the two critical values. So we're going to make our sign chart here. And now we're going to put the values on my sign chart. I got to be careful that I don't just put negative 7 and 1 on here, but I also need to put negative 3 on here, because that's a restriction on the domain. And something weird could be happening there at negative 3. And so I want to make sure that I'm careful about what's going on there at negative 3. So when I first choose a value, the first thing we're going to note is before I pick these values, this denominator here of my derivative is always a positive number. And since that's always a positive number, then I can really just ignore it when I'm evaluating on these intervals. So if I pick something between negative 3 and 1, like 0, I end up with a positive and a negative here. Right? So positive times a negative is going to be a negative. And again, remember, we're still dividing by this positive, but that doesn't affect anything. And then if I pick something more than 1, like 1,000, I'm going to end up with two positives here, which makes a positive. If I pick something like negative 5, that's between negative 7 and negative 3, I get a positive and a negative, which is negative. And if I pick something less than negative 7, like negative 1,000,000, I end up with two negatives, which makes a positive, which tells me that my function goes from increasing to decreasing to continuing to decrease to increasing. And so now we just need to find the values of my function at negative 7 and at 1, and those should be my local max and local min values, right? A local max at negative 7 and a local min at 1. So in order to do that, we'll just take this to another page here. And we're going to have function. There we go. There's our page. We're going to have our function, which was x squared minus 2x plus 1 over x plus 3. And then we need to evaluate to find f of negative 7 and f of 1. Well, if I plug in negative 7 to that, I get 49 plus 14 plus 1 all over negative 4, which looks like that comes out to be, what, 64 over negative 4, which is negative 16. And if I plug in 1, I get 1 minus 2 plus 1 over 4. Well, 1 minus 2 plus 1 is just 0, so that's 0. And so from our sign chart, we should be able to see that we have a local max of that negative 16 value, which seems a little weird that the max is negative 16, but if we look, that is what's happening at negative 7. That's a local max. So we have a local max of negative 16 at x equals 7. Sorry, negative 7. And we have a local min of 0 at x equals 1, which seems a little counterintuitive, right? That the max is smaller than the min, but that's because of that discontinuity that we have at x equals negative 3. It's kind of messing things up there. So when we talk about the intervals on which this thing is increasing, right? It's increasing, well, we were increasing on the interval from negative infinity to negative 7, and again from 1 to infinity. So that's negative infinity to negative 7, and 1 to infinity. When we talk about the decreasing intervals, it was decreasing on all the other intervals, right, from negative 7 all the way to 1, but it's not decreasing at negative 3 because the function doesn't exist at negative 3. So we still need to break that up into two different intervals. We'll say from negative 7 to negative 3 and from negative 3 to 1. All right, for our next one here, we are going to take a derivative again. So we have f of x equals e to the x times x squared minus 3x plus 1. Our derivative here, f prime of x, is going to be done with the product rule, e to the x times 2x minus 3. Right? So that's the function times the derivative of the second, and then plus the derivative of the first, e to the x, times x squared minus 3x plus 1. I can factor an e to the x out of that, leaving me with x squared minus 3x plus 2x, which would be minus x, and then minus 3 plus 1, which would be minus 2, which gives me e to the x times x minus 2 times x plus 1. And from there, we should be able to easily see that this is never undefined. Right? So f prime is never undefined, but it does equal 0 when x is 2 and x is negative 1. And I can kind of ignore this e to the x value because e to any power is never going to equal 0. So we got x equals 2 and x equals negative 1 as our critical values. We'll need to do two things. One is make a sign chart with those. So there's negative 1 and 2 on my sign chart. My original function didn't have any discontinuity, so I don't have to do anything weird with that sign chart, put any discontinuities on it. If I plug in something between negative 1 and 2, like 0, well, e to the x is always positive, so I can kind of just ignore that, right? But the 0 minus 2 is negative, and the 0 plus 1 is positive, so I got a negative times a positive is a negative. If I plug something like 100 in, something more than 2, I get two positives, which is going to give me a positive. And if I plug in something like negative 1,000,000, I'm going to get the two negatives. So I'm going to still get a positive value here, which tells me that my function goes from increasing to decreasing to increasing. And now we just need to figure out what the actual max and min values are by evaluating for f of 2 and f of negative 1. Well, f of 2 is just e squared times whatever we get if we evaluate x squared minus 3x plus 1 and 2, which is 4 minus 6 plus 1, which is just negative 1. So that'd be negative e squared. And then we need to find f of negative 1. Well, f of negative 1 is e to the negative 1 times, well, negative 1 squared is 1. 1 plus 3 is 4, plus another 1 is 5. So this is 5 over e. So we've got a local max at negative 1, and the value at negative 1 was 5 over e. So a local max of 5 over e at negative 1. We've got a local min of negative e squared at x equals 2. We are increasing from negative infinity until we get to negative 1. And then again from 2 to infinity. And we are decreasing on the interval from negative 1 to 2. And that should be our final answer. All right, for number 5 here, we're looking at x squared minus 1 over x squared plus 2. This is again going to be a quotient rule problem. So we'll take our derivative, f prime of x is v, denominator, times du, 2x, minus u, our numerator, times derivative of v, which is also 2x, all over x squared plus 2 squared. A little bit of simplification there, and we can see that this is going to be a 2x cubed, and this is going to be a 2x cubed, and there's a minus sign in between them, so those are going to cancel. And we're going to have a 4x minus a negative 2x. Well, 4x minus a negative 2x ought to just be 6x. So this is 6x over x squared plus 2 squared. And I think we can recognize that that's never going to be undefined. There's no domain restrictions here, right, on x squared plus 2, because x squared plus 2 is never going to equal 0, because that'd be x squared equals negative 2, and that yields imaginary results. So we could see f prime is never undefined either, because we have that same situation there. And so f prime equals 0 if 6x equals 0, which just means x is 0. That makes life pretty easy for this one. We'll just go in and make a sign chart with 0 on it. If we plug a positive number into our derivative, we get a positive number from 6x, and this denominator, which is always positive. So positive over positive is positive. If we plug a negative number into our derivative, we get a negative from the 6x, but still a positive from the denominator, which gives us a negative, which tells us, since f prime goes from negative to positive, f goes from decreasing to increasing. We'll need to figure out what the value of the function is at 0. Well, that's pretty straightforward. The x squareds will just kind of go away when x is 0. We end up with f of 0 equals negative 1/2. And we can see that it's a local min of negative 1/2 at x equals 0. And we can see that we are decreasing from negative infinity to 0, and that we are increasing from 0 to infinity. And we can see that very nicely from our sign chart. All right, our next one here is a little more complicated function, sine cubed x times cosine x. We do have a restriction on our interval this time, which is nice, because otherwise we'd have an infinite number of critical values. So we're going to only talk about from 0 to 2 pi, and we're going to just talk about an open interval from 0 to 2 pi. So we'll take a derivative to start. That would be a product rule problem. So it'll be sine cubed x times negative sine x. And then we'll add to that the derivative of sine cubed, which is 3 sine squared x cosine x, using the chain rule, like u cubed, where u is sine. And then we have to multiply that by the other cosine x, because that's our second function. So simplifying that down, we should see that that just turns into a sine. We'll put this one first, the second one first. 3 sine squared x cosine squared x minus sine to the 4th of x. And that's never undefined, because sine and cosine are defined for all real values, right? F prime is never undefined. But when does it equal 0? Well, we'll have to factor out the sine squared from it first. So sine squared x times 3 cosine squared x minus sine squared x is equal to 0, right? And so then basically what we're looking at here is, well, sine squared x equals 0. That's when sine of x is 0. That'd be when x is 0 or pi or 2 pi or so on. The only value on my interval that I care about here is going to be the value at pi, right? Because we're only talking about the open interval 0 to 2 pi. The 3 cosine squared x minus sine squared x is a little more difficult to deal with. If we set that equal to 0 and then add sine squared to each side, we get this. 3 cosine squared x equals sine squared x, or 3 equals tangent squared x, if I divide both sides by cosine squared. Well, that tells me that tangent x equals root 3. And there are multiple times, in fact, actually not just root 3, but plus or minus root 3. And don't forget the plus or minus when you square root. So there are multiple times between 0 and 2 pi when tangent is equal to positive or negative root 3. Those are all the intervals of pi over 3 going around the unit circle, right? Except for 3 pi over 3, right? Because the tangent of pi is just 0. So that's going to be, not tangent, but that's just going to be x is equal to pi over 3. X is equal to 2 pi over 3, 4 pi over 3, and 5 pi over 3. So we end up with 5 different critical values. We'll need to make a sign chart for them, so we'll see if we can fit that in over here. We're going to start at 0, we're going to end at 2 pi, and we're going to make sure that we get everything in there. Pi over 3, 2 pi over 3, pi, 4 pi over 3, and 5 pi over 3. And the easiest way to think about this is just picking values that that we know are going to be in like the appropriate quadrants here. So like if I pick something in the first quadrant for between 0 and pi over 3, right, I mean, sine is always positive. And sine squared is always positive. So I'm just going to kind of ignore this anyway. Sine of any angle squared is going to be a positive value. So really all I care about is 3 cosine squared x minus sine squared x equal to a positive or a negative value. Well, if we plug in something like pi over 6 into that, right, the pi over 6 value, that gives us, I'm not going to necessarily go through all the arithmetic here. We'll do it a little bit for the first one. So 3 times the cosine of pi over 6, which is root 3 over 2 squared, right, minus the sine of pi over 6 squared, which is 1/2 squared. I mean, I think we can pretty obviously see that that's going to come out to be a positive value. So this is going to be a positive value. If I plug in something between pi over 3 and 2 pi over 3, let's say something like pi over 2, right? Well, we know that the cosine of pi over 2 is 0. So this is just 0 minus the sine of pi over 2 squared. That's a negative value. And if we keep plugging these in, I'm not going to go through the arithmetic and doing all of them. We're just going to see that it's going to switch for all these values in the first and second quadrant. Like that one's going to be a positive value. But then when I go into something like the values between pi and 4 pi over 3 in the third quadrant, where all of this stuff is negative, these values are just going to repeat again. Right? We're going to get a positive here, a negative here, and a positive here. And you can test values on your own if you want to for that, but I'm not going to do all the trig work right here. But that's what you end up with. And we do need to figure out the value of our function at all of these places. So let's do that real quick. We need to find f of pi over 3. Right? And f of pi over 3, and these are all going to come out pretty similarly because we're pretty much looking at the same values except positives or negatives. F of pi over 3 is going to be root 3 over 2, that's the sine of pi over 3 cubed, times 1/2. Well, that just becomes 3 root 3 over 16. And f of 2 pi over 3, well, 2 pi over 3 is in the second quadrant. That makes it a negative value. But otherwise, the root 3 over 2 and the 1/2, those aren't going to change. And the only thing that changes is the value of cosine. And in the second quadrant, sine is still positive, but cosine is negative. So this is going to be negative 3 root 3 over 16. And f of 4 pi over 3, well, in that quadrant, that's the third quadrant, right? Sine and cosine are both negative, so we're going to end up with a negative times a negative, which is a positive. And in the fourth quadrant, when we do 5 pi over 3, it's going to flop back to being a negative because we're going to have a negative value for the sine, but a positive value for the cosine. And then lastly, we still need to figure out what's f of pi. Well, conveniently, f of pi is just going to be, well, actually, we don't even really need to figure out f of pi. I was going to say it's going to be 0, but it doesn't really matter, right? Because sine of pi is 0. But that doesn't really matter because what was happening at pi, right? We increased, decreased, increased, continued increasing, decreased, increased. So there wasn't actually a max or a min at pi, so we don't need to find the value of the function at pi. So in the end here, now that we've kind of gone through all this stuff, we'll need a new page here. We had a local max of 3 root 3 over 16, and that occurred at both x equals pi over 3 and x equals 4 pi over 3. And we had a local min of negative 3 root 3 over 16, and that was at x equals 2 pi over 3 and x equals 5 pi over 3. And we can look back at our sign chart, we could see, right, we had the max at pi over 3 and 4 pi over 3, and the mins at 2 pi and 5 pi over 3. And those were the values we got. And then we were increasing, looks like from 0 to pi over 3, and from 2 pi over 3 to 4 pi over 3, and from 5 pi over 3 to 2 pi, and then only decreasing on the other two intervals. So we'll write that out. We are increasing. Since it's an open interval, we'll start on 0 with a parenthesis, 0 to pi over 3. And then our next one was from 2 pi over 3 all the way to 4 pi over 3, because remember, 0 was a critical value, but it didn't turn out to actually be a max or a min. And then from 5 pi over 3 to 2 pi, and 2 pi was the end of the open interval, so we'll use a parenthesis. And for our decreasing interval here, we just had what was left, which was pi over 3 to 2 pi over 3. And we also had 4 pi over 3 to 5 pi over 3. And so that's our intervals, that's our local max and min, and that ought to be good for that one. So for this next one, we're just going to do the same thing. We're just going to take a derivative here of this. Right, if I take the derivative here of e to the 2x minus e to the x, I get 2e to the 2x minus e to the x. And we know that e to the 2x, that's the same as e to the x times e to the x, right? Because you just add the exponents. X plus x is 2x. So I can factor an e to the x out of this, giving me e to the x times 2e to the x minus 1. And we'll note that our derivative is never undefined. But we'll also note that it does equal 0 when either e to the x equals 0, which is never, or 2e to the x minus 1 equals 0. Well, that gives me e to the x equals 1/2, or x is equal to the natural log of 1/2, right? Because if I take the natural log of both sides of this, the natural log of e to the x is just x, and then the natural log of 1/2 is the natural log of 1/2. And usually I'll rewrite natural log of 1/2. There's a couple ways to think about how to rewrite it, but if you think about it as natural log of 1 minus natural log of 2, well, the natural log of 1 is just 0. So that's negative natural log of 2. So it looks like we just have one singular critical value here, negative ln of 2. And so here's negative ln of 2. And it should be, I think, fairly straightforward for us to figure out what's happening with our function here on our sign chart, right? Even if we're not sure what the natural log of 2 is, whether we're not even sure if it's positive or negative, which we should know it's natural log of 2 is positive, so negative ln of 2 is a negative number. All we have to do is really just plug in a really, really big number like 1,000,000. And I think we can see that like the e to the 2x in our derivative is going to dominate the e to the x. Or if we look down here, it's 1,000,000, e to the 1,000,000th power times 2e to the 1,000,000th power minus 1. Clearly a positive times a positive, which gives us a positive. And on the other side, if we put in negative 1,000,000, right, this number becomes infinitely small, close to 0. And we subtract 1, we get a negative. And then this is still positive, so it's a positive times a negative, which is a negative. So we can see that our function, f, decreases and then increases, right? That's what f is doing. And so we just need to evaluate what is f of the natural log of 1/2, or f of negative ln 2, which is just going to be e to the negative 2 ln 2 minus e to the negative ln of 2. And if we try to evaluate that out, we can remember that like this negative 2 and this negative 1 are like exponents. They kind of get undone. Right? This becomes e to the ln of 2 to the negative 2, which is 1/4, minus e to the ln of 2 to the negative 1, which is 1/2. Well, that just becomes 1/4 minus 1/2, or negative 1/4. So that's our value of our local minimum. We see it's a minimum because the function decreased and then increased. So we'll write this out on a new page. We've got a local min of negative 1/4 at x equals negative ln 2. And then we were decreasing from negative infinity to the negative ln of 2, with a bracket, of course, on that. And then we are increasing on negative ln of 2 to infinity. And that's it there for number 7. So for our next one here, we're just going to use the same process. We're going to take our derivative. And since this is natural log of u, it'll be 1 over u times the derivative of u, where the derivative of x squared is 2x, the derivative of the minus x is 1, and then the plus 2 goes away because it's a constant. When we set this equal to 0, we just need to set the numerator equal to 0, which gives us x equals 1/2. And if we think about trying to set the denominator equal to 0 to figure out when it might have places where the derivative is undefined, we don't really need to do that, because we should recognize that if something's inside a natural log, like this is in our original function, right, the thing inside the natural log has to either be positive, or it has to be positive. It can't be 0 and it can't be negative. So anything that will make this equal 0 is already restricted from the domain of our original function up here. So it would be good maybe to at least make sure that they're, figure out what the actual domain of this is, right? And so if we look at this to try and figure out when this thing is equal to 0, we can see that the discriminant of it, b squared minus 4ac, is equal to, maybe we get negative 1 squared is 1 minus 4 times 1 times 2. Right? We get a negative 7 here, which means that this doesn't have any real solutions, which means that it doesn't have any x-intercepts, which means it's lying entirely above the x-axis, which means that the values of x squared minus x plus 2 are always positive numbers. Right? And so if that's the case, then we know that there's no discontinuities in our original function whatsoever. Right? So we don't have to worry about any extra stuff to look at here. So then we can just go ahead and make our sign chart using only 1/2 in our derivative. So we'll plug in something more than a half, like 1. And we already just decided that this is always positive. So all we really need to do is look at the sign of the numerator. If I plug in 1 to the numerator, to 2x minus 1, I get a positive number. And therefore, this becomes a positive, which means that f is going to increase. And if I plug in something less than a half, like 0, or when I plug in 0, the numerator becomes negative, and the denominator is still positive, so that becomes a negative, and f is decreasing. And so all we have left to do is just figure out what the value of f of 1/2 is, so that we can actually write out what the local minimum is, and our increasing and decreasing intervals after that. So f of 1/2 is just the natural log of 1/2 squared, which would be 1/4, minus 1/2 plus 2, which, well, 1/4 minus 1/2 is negative 1/4. And if you add 2 to that, you get 7/4. So this is just the natural log of 7/4. So we can say that we have a local minimum of ln 7/4 at x equals 1/2. We can say that this function is increasing on the interval from 1/2 to infinity, and that it's decreasing on the interval from negative infinity to 1/2. And of course, it's good that we checked the domain, because if there were domain restrictions on it, then we wouldn't want to say that it was increasing or decreasing towards negative or positive infinity, because it might not be doing that. But in this case, we checked that domain, and it is. All right, for our next one here, our second to last one, now we're looking at the inverse tangent of x squared minus 2x. So first thing that we'll do is we will take our derivative, and we can also think about the domain. We know the domain of inverse tangent is all real numbers, so we can plug anything into the inverse tangent, so there's not going to be any inherent domain restrictions on this. So when we look for our derivative, we're just going to do the rule for inverse tangent u, which is 1 over 1 plus u, which in this case is x squared minus 2x squared. And then, of course, because of the chain rule, we have to multiply that by the derivative of x squared minus 2x, which using the power rule is just 2x minus 2. And if we look at this, if we think about the denominator of this, I think it's pretty obvious that the denominator of this thing is never going to equal 0. Right? I'm not even going to rewrite this into like the 4th degree function that the denominator could be, because I know that 1 is positive, and I know that something being squared is positive. If I add 2 positives, I get a positive, which means I'm never going to get 0 out of that. So this is never going to be undefined. And really all we need to do is see when f prime of x equals 0, which would be when the numerator is equal to 0. Well, 2x minus 2 equals 0 when x is equal to 1. So we've really just got a singular critical value again, just like the last one. We'll make a sign chart for f prime, putting 1 in the middle of that sign chart. And we already said that the denominator of this is always positive, so really all we care about is what happens to the numerator. If I plug in a number more than 1, like 1,000, into that numerator, I get a positive. And if I plug in something less than 1, like 0, I get a negative, which is going to tell me that my function decreases and then increases. So we'll just evaluate what f of 1 is. Well, f of 1 is the inverse tangent of 1 squared, which is 1, minus 2, which is the inverse tangent of negative 1. Well, the inverse tangent will only output values between negative pi over 2 and pi over 2. So we should recognize that the inverse tangent of negative 1 then must be negative pi over 4. We know that the tangent of 3 pi over 4 is also equal to negative 1, right? But we need the value that's in the 4th quadrant, that is between negative pi over 2 and pi over 2, which is why we get negative pi over 4. So we'll say that we have a local min of negative pi over 4 at x equals negative 1. We'll say that we are increasing from 1 to infinity, and that we are decreasing from negative infinity to 1, because that's what it shows on our sign chart. All right, here is our last one. We've got the cube root of x cubed minus 3x plus 2. So first off, we'll think about the inherent domain restrictions, which there are none, because we can cube root any number. So really all we need to do is just take a derivative. So our derivative will use the chain rule on that, right? This is u to the 1/3, so that'll be 1/3 of u to the negative 2/3. And then we'll multiply that by the derivative of u. The derivative of x cubed is 3x squared. The minus 3x becomes minus 3. And the plus 2 is a constant, so it goes away. So when I drop that down to the denominator, I can see, I think that the 3x squared minus the 3 and the 1/3 here, those 3's can all cancel out. So we just end up with x squared minus 1 over x cubed minus 3x plus 2 to the power of 2/3. And so we should be able to tell pretty quickly that the numerator is equal to 0. So f prime of x equals 0 if x squared minus 1 equals 0. Well, x squared minus 1 equals 0 when x is plus or minus 1. So there's 2 critical values. But then we also need to see when it's undefined. It'll be undefined if the denominator is equal to 0, right? Because we can square anything and cube root anything. So it's never going to be undefined for like a radical or something, but we know that it could equal 0. So we have to check, when does x cubed minus 3x plus 2 equals 0? Well, we may not immediately right off the bat know how to factor this, but what we need to do then is just recognize that we can use the rational root theorem here. We look at the factors of the constant, so the factors of 2 are positive or negative 1 and positive or negative 2. And then we look at the factors of the leading coefficient. The leading coefficient is 1, so its factors are just positive or negative 1. And the quotient of these two things, 1 over 1 and 2 over 1, are the only 4 options for rational roots of this. So we'll try out 1 first, remembering that we need to put a 1 for the 1x cubed, a 0 for the 0x squared, a minus 3 for the minus 3x, and a 2 for the constant. And then we'll use synthetic division just to test this out. If our final term down here becomes a 0, then we know we've picked the right factor. So remember synthetic division, we drop the 1 down first from the 1x cubed. When it's below the line, we multiply what's in the box and put it in the next column. And when we have two numbers above the line, we just add them together. A number below means multiply, 2 above means add, then multiply, then add. We can see that we did end up getting 0, which means that 1 was the right choice here, or was a right choice. There might have been another one. So what we can do then is we can rewrite this as x minus 1, right? Because if I have a 1 up here, that means that 1 is a root of this function, so x minus 1 must have been a factor. And then I multiply it by the 1x squared plus 1x minus 2. And that equals 0. And the factor that I end up getting here, when I factor this even more, I can multiply this out again and say this is x plus 2 and x minus 1. And so we can see that we get x equals 1 and x equals negative 2 as our critical values there. So the 1 is an overlap, so we're still going to use 1. And then we have a negative 1 and we have a negative 2. So we've got 3 different critical values that we're going to work with here. So we're going to make our sign chart for these, and we'll do this on the next page. So our derivative, once again, f prime of x was x squared minus 1, and I'm going to rewrite that as x plus 1, x minus 1, right, just so that it's easier for me to look at it. And then in the denominator, we have the x squared minus 3x plus 2, sorry, x cubed minus 3x plus 2 to the 2/3 power. And I'm not really going to worry about that denominator because I know that this is always a positive. It's always greater than 0, right? If I take some number and cube root it and then I square that, when you square something, you always get a positive. So really all I care about is what's going on with the numerator here. And so on my sign chart, I'm going to put my 3 critical values of negative 2, negative 1, and 1. And when I plug in something, let's start with something less than negative 2, like negative 1,000,000, I'm going to end up with a negative and a negative from this. And 2 negatives multiplied together makes a positive. If I plug in something between negative 2 and negative 1, like negative 1.5, the first term, negative 1.5 plus 1 is a negative. And the second term there is also a negative. So I end up with a positive again. Then if I plug in something between negative 1 and 0, like negative 1 and 1, like 0, I get a positive times a negative, which is a negative. And if I plug in something more than 1, like 1,000,000, I get 2 positives, which is a positive. So we can see that what's happening here is our function f is increasing, then it continues to increase, right? And then it decreases, and then it increases. So we've got one local max, and we've got one local min. We don't need to evaluate for what it equals at negative 2. We just need to evaluate what our function, which was f of x equals the cube root of x cubed minus 3x plus 2. We need to evaluate that at f of negative 1 and f of 1, because that's where our local max and our local min occur. So f of negative 1 is just the cube root of negative 1 cubed, which is negative 1, and then plus 3, and then plus 2. So we end up with the cube root of 4. And for f of 1, we've got the cube root of 1 minus 3 plus 2. Well, that's just 0. So f of 1 is 0. So now we're ready to write out our answers here. It looks like we've got a local max of the cube root of 4 at x equals -1. We've got a local min of 0 at x equals 1. And our function is increasing on the interval from -infinity all the way through -2 until we get to -1. So we don't need to break it up at -2 because it continues to increase through that. And then it's increasing again from 1 to infinity. And our function decreases only on that singular interval where we showed it was going down, which was from -1 to 1. And that's the end of our walkthrough for this homework assignment. And yeah, we're going to do some more stuff with some more difficult functions and the second derivative next time.